Hello, physical science students. This is the last section in this unit, and we are going to look at 3 more applications of Newton's laws. We're going to look at centripetal force. We're going to look at what happens in a collision. And we're going to ask this question, how are rockets propelled? We'll start with this idea of centripetal force. Centripetal force is simply the force that is exerted toward the center of a curved path. Let's look at a few diagrams showing this. Here we have a person holding a ball on the end of a string and twirling it around. The centripetal force is the force exerted toward the center of that curved path. Here's the curved path. The centripetal force is going, if the ball is over here, the centripetal force would be this direction. If that person were to let go of this string right here at any point, the object would no longer be experiencing centripetal force, and it would continue to travel in a straight line like this, straight out at an angle exactly perpendicular to the centripetal force where it once had been. So at the release of that object, it will continue to travel in a straight line perpendicular to the last moment that it experienced the centripetal force, pulling it in. You can see that in this diagram. As this object is traveling around, it has this velocity in this direction and a centripetal force in this direction at this point. It's traveling around here. Its velocity at this point actually is this direction, but the centripetal force is in this direction. And as it's traveling in this curved path, at every moment in that curved path, that velocity is perpendicular to the direction of the centripetal force. So here are some examples of centripetal force. Centripetal force keeps the Earth in orbit around the sun. And just as we said, the centripetal force is in this direction, toward the sun, from the object toward the sun. The velocity is in this direction, perpendicular. The force is in this direction. The acceleration is in the same direction as the force as well. And centripetal force keeps this car on the road. In this case, it's the friction between the tires and the road that are creating that centripetal force to keep the car on the road. Centripetal force keeps the passengers in the ride. And the force acting as a centripetal force here would be the seat backs here that is keeping these passengers in the ride. It is the force being exerted toward the center of that ride, keeping the passengers from flying out at a perpendicular direction with their velocity off of that ride. You may have heard this word before. It's centrifugal force or centrifugal. We get our word centrifuge from that, if you've heard of a centrifuge. And centripetal force, remember, is the force that is pointing in toward the center of the curved path. Is there such a thing as centrifugal force? Those people who are, say, on that ride, they feel like they're experiencing this force that is making them go away from the center, right? There is no such thing as centrifugal force. Big X, no centrifugal force. It's an incorrect use of this word force. What is being experienced on this ride is a lack of centripetal force. That would be centrifugal force. But it isn't an actual force. It's not a real force. So when you see that word, it's being used incorrectly. If those people did not have the back on their ride right here, they would fly off that ride. But the reason they would is because they are traveling at a velocity that is perpendicular. I don't know which direction is this, the red going this way. They're traveling at a velocity that is perpendicular to the acceleration, which is toward the center. The acceleration is toward the center, their force is toward the center, their velocity is perpendicular to that. So if that back were not there, they would continue to travel in that straight line, and that's what they are feeling. That's what they are experiencing. There is not a force somehow that is sucking them away from the middle of the ride. So this is not a real thing. Remember that inertia resists the force that maintains circular motion. So another application here is that, let's say you have a ball attached to the end of a string and you're twirling it around. As you are twirling it around and around, it will begin to become more difficult to hang on to. You can try this, that you'll see, just in case you have never tried that. You probably, everyone has tried it, but if you haven't, try it. The faster you twirl it around, it gets harder to hang on to. That's because you are needing to exert more and more centripetal force. Remember, force pulling in toward the center of the curved path in order to keep that object in place. If you do not exert enough centripetal force, this object will continue at its straight velocity off on an angle tangential to this curve. So the greater the mass, the greater the acceleration, the more centripetal force you need to use to keep that object in orbit. Next question, what happens in a collision? This is a really exciting topic because we get to talk about momentum and what momentum is, and the fact that momentum, just like matter and energy, is conserved. The total does not change. As long as there are no external forces acting on the group of objects. If we have external forces, well, then we cannot account for the total momentum. But if we have no external forces, momentum is conserved. An example would be Granny here. Granny is colliding with this little boy. And Granny here beforehand is going at a velocity that is considerably faster than this little boy. I'm not sure if he's standing still or just going really slow. But as she collides with him, their total momentum over here is going to be the same as the momentum was here, assuming negligible friction with the roller skates. Momentum is always conserved. So let's just look at a little example here with these balls. Let's say we have a situation here where this ball has just been hit and it is traveling up in this direction with an initial momentum, P is momentum, of 3 kg/meters per second. This yellow ball has not been hit yet, not collided with, so its momentum, initial momentum, the little subscript I, is 0 kg/meters per second. Now let's see what happens once a collision occurs. After this ball strikes this ball, the two balls will then each have a new momentum. If we write down their final momentums, we see the final momentum of this yellow ball, it will go in this same upward direction, 4 kilograms times meters per second in that direction. This ball, the momentum, bounces back and goes in the opposite direction, 1 kilogram/meter per second. We can look at the total initial momentum. So if we do that, let's look at the initial momentum total. We'll call it initial total. Is going to be equal to 3 plus 0, which is 3 kilogram/meters per second. And if we look at the momentum, the final momentum total, hard to write so tiny here, it is going to be 4 minus 1, because the 1 is in the opposite direction. It's going to be a negative number. It will also be 3 kilogram meters per second. And so momentum is conserved. It was the same total before and the same total after. One more thing to look at before we leave this idea of momentum and force and collisions is the relationship between momentum, force, and time. Remember Newton's second law, force equals mass times acceleration. If we take that and we also take what we know about momentum, momentum equals mass times velocity, and we incorporate these two formulas together, we know that force equals mass times acceleration. Acceleration is just the change in velocity over time. So I'm just substituting that in. Mass times the change in velocity is going to be final velocity. Minus final velocity minus initial velocity over time. And now I can substitute, I know that, well, not really substitute, I'm simply going to multiply this mass by each item within those parentheses. So if I do that, I get mass times final velocity minus the mass times the initial velocity, all divided by the time. That equals force. I can look at this equation and analyze it to help me understand the relationships here. I can see that my change in momentum here, mv is momentum, remember, m times v. So my change in momentum, the final minus the initial, is going to depend on the force and the amount of time that that force is exerted, the length of time. I can see that if I have a really large force and a very short amount of time, that could give me the same change in momentum as a really small force with a large amount of time for a longer period of time. So those are definitely all related. Just an FYI, this actually is how Newton originally wrote his second law of motion, was in this format rather than our very simple F equals ma. Now let's look at our last question. How are rockets repelled? And this is just a combination of some of these things we've already been talking about with conservation of force and momentum. Let's look at some of the forces at work here first. Let's look at the force of the rocket engine, that is the force that is exerted on the hot gases that are being produced by fuel being burned. Right here, this arrow represents the force of the rocket on those gases. There's also the force of those expelled gases back on the rocket. This is the force that is propelling the rocket forward or up. Momentum is also at issue here, and we're going to see how momentum is conserved. If we talk about the initial state of the rocket and the fuel, the total momentum is 0 because the rocket and the fuel are both initially at rest. When the fuel is burned and the hot gas is expelled, the gas travels backward with momentum, mass times velocity. And additionally, the rocket travels forward with a momentum, a mass times velocity momentum. These momentums are equal in size but opposite in direction, so our total momentum is still 0. Also, the people controlling this, they can control how much gas is ejected and the gas's velocity so that the rocket's motion can be controlled. And that's how that works. Advanced ideas. You show me how mathematically how force equals mass times acceleration can be equivalent to the idea that force equals the change in momentum divided by the change in time. Go ahead and show me that on your own, and I'm not requiring that you know how to do that, so that's an advanced idea. You could also design a project that demonstrates main ideas behind the concepts of force and momentum. Explain your project in writing or orally, show it to the rest of the class, or just show it to me, whatever you feel like doing, and I look forward to seeing your ideas.